What's going on, everybody? Mr. Diamond back here, and we're going to be doing angled projectile motion. So it's going to be a little bit different than the projectile motion that we did. The ideas are still going to hold the same, but this is going to be examples of things like football. We're gonna do a football here. I'm going to draw a nice little kind of that. And I've actually got a brown pen around here. Don't nobody ever tell me that Diamond doesn't like sport. So got my nice little brown football going on right there. Oh, the brown doesn't even show up, of course. It's brown, I promise. Well, I know what color footballs are. I swear. Man, you still can't even tell. Whatever. Moving on. And we're going to, instead of just it being projected horizontally like we did in our other example problems, now it's going to be kicked. And so it's going to go up and it's going to come back down in this kind of nice arc pattern that it's going on. Because of the influences of gravity, if we were to stop and look at the vectors of the velocity in the y direction at each of these points, they would be going up and up and up, but they would slowly be decreasing until they got to the very top part here, and then there would be no velocity vector in the y direction, just like whenever we tossed a ball in the air. And then the velocity vector would slowly flip and get longer and longer and longer and longer, pointing downwards as it goes on the other end, as the object falls to Earth. Just like before, we're going to pretty much just be resolving whatever this initial speed is into vector components, and it'll make it more manageable. And then from there, we're going to, sure. Don't worry, I didn't die. For any of you that thought that this random interruption was just me dying, you may have heard that there was ice cream, and there was, in fact, ice cream. Man, that looks disgusting under that light. Oh, man. It's an orange dreamsicle. It's not actually yellow in color. Some weird lighting changes. I've missed every one of these, like, reward things they're bringing for the teachers. Like, they brought little bags of chips and, like, sodas and stuff like that, but I'm always recording, and so I apologize for that gap. I wanted to get it finally for once. So anyway, back to actual physics, because there's no such things as multiple takes, so I can't re-record this. Usually you're going to want to resolve your vector into its components. It'll make it more manageable. So we could take this component that it was kind of pointing up here and at least get your initial speeds into an x and a y component. And once you've done that, well, it's basically the same as these other example problems that we were working. The other example where we had an x that was constant and then a y that was slowly going down. We're just, instead of starting here at the curve, we're now going to have to actually figure out where that point is at. Or maybe not, depending on what the question is actually asking. To do this, we are going to need to use our trig skills. So nothing crazy there. The example we're going to use is we've got our football here. So now I'm going to redraw it so you can actually tell it's brown, so you know that I do know sport and am good at sport. I'm not good at sport. Don't let me lie to you like that. I hope you were about to call me out. All right, das Football is complete. And it's going to be kicked at an angle. So it's going to be kicked at an angle. And that angle that we're going to use as our example is going to be 37 degrees above the horizontal. And it's going to have a velocity of 20.0 meters per second. We're going to assume no air resistance, no spin, and that the football is, we're going to assume it's leaving the ground, and it's going to come back up. We're going to calculate three things. we want to calculate max height. We want to calculate time to hit the ground. And we're going to want to calculate, see how far does it go? Question mark. Okay, so we've got a couple of different things that we're going to want to do first. The main thing, though, is going to be we're going to want to resolve this into its components. That's going to make everything way easier, and we'll help finish the second step that we normally do in a problem first. So here I've got, I have all these colors. I should probably use them. So here we've got our x component. Here we've got our y component. So for our x component, that is adjacent. So we're going to use adjacent hypotenuse. That's cosine adjacent hypotenuse. If we want to get just the adjacent part, we're going to do hypotenuse times cosine theta equals adjacent. So we're going to do 20.0 times cosine 37. Plug that bad boy into our calculator. 20 cosine 37. Let me put that back on here so you guys can see it. That would probably be a good idea. At least sort of see it. So I've got 15 point, we're going to just call that 97 meters per second. So that's in our x direction. And then in our y direction, which I used blue for. Also, I'm not entirely sure why I did that further down there. I guess it was just to irritate some of you. So we're going to do we're going to use hypotenuse times sine theta equals opposite. So we're going to do 20.0 sine 37. We'll get that number. I like to just hit second enter and then back up and change it to sine. So we've got 12.04. We'll round it there. 12.04 meters per second. So now that we know this information here, we can actually start listing out the rest of our information. So let me really quick No, that was of utmost of importance. I had to put my ice cream in the freezer because this is a long example. We're going to go ahead and figure out our information. Now, the first question is to the max height. So we've got our football, and we're trying to figure out up there. We're going to assume, so this is for A, we're going to start at the beginning, and then we're going to go to at the max height. Now, let's figure out our information. Well, we know our initial y position. Our initial y position is 0. Let me scooch this so we can see a little better. We don't know our final y position. We know our initial v in the y direction is the y direction velocity right here. It's 12.04. We also know, that's not 0. That's what we're looking for. We also know that just like with our last example, when you're at that midpoint of the arc, that is where it freezes. It stops going up or down, and it's just for that brief moment, it's going to have a final y velocity of 0. And then we know our acceleration is negative 9.8 meters per second. So with all that information, we should be able to figure out what our y is. And looking at all of our information that we've got here, it looks like our easiest example or our best equation to use is probably going to be our x equals x naught plus v naught t. But we don't have t. That's probably where your brain like jumped. And I definitely did not just cover my butt because I realized we didn't have t. So since we don't have t, we're going to actually have to use the other one right here. We're going to have to use v squared equals v naught squared plus 2a x minus x naught. Okay, so we got vy squared equals v naught y squared plus 2ay y minus y naught. And then we can cancel out some of this stuff. We can get rid of that to 0. Our v naught in the y direction we have, but our final is going to be 0. And we also know our acceleration. We know that, so we've got all the information that we need there. So let's go ahead and rearrange it a little bit. And to rearrange it, we're going to we'll get negative v naught y squared, because we have to subtract that to the side, over 2a in the y direction. That's going to equal our y. So we're going to get negative. Our v naught is 12.04 squared over 2 times negative 9.8. Plug all of that in. (12.04 squared) negative answer over 2 times negative 9.8 equals 7.396 meters. I don't know why I erased the first meters. Then for sig figs, I gave you everything has 2 or 3. We'll just go ahead and call this one 3. So we'll do 7.40 meters. So 7.40 meters, not too bad. Okay, next we've got B. Now, there is a couple of approaches to figure out B. The easiest one is also the one that takes the most mental kind of gymnastics and like logical conclusions that you have to jump to. And that involves remembering that when we did our parabolic motion, if you know the velocity that something is leaving at, and if it's landing back on the same flat level, you can actually know that whatever kind of pieces line up across this parabolic motion up here, because it's parabolic, this point and this point, the same distance away from that peak, is going to have the same speed, and then the same speed, and then the same speed all the way across. So whatever speed it vertically left with is actually also going to be its final if we are at the end. So what we're going to do here now, so now we're going to do at the end. So our y position, or our final y position, our initial y position is 0 meters. Our final y position is also 0 meters. Our initial y velocity is 12.04. Our final y velocity is negative 12.04. And our acceleration is negative 9.8 meters per second squared. Now, if this doesn't make sense to you, or this feels like you would never logically get to this without me explaining it, you could also solve for time up here. So alternative method, I'm going to write it over here. Alternative, solve for midpoint time. So you can use that information up there to solve for the time at the midpoint and then just double it. Or I'm just going to plug it in with this information right here, and we're going to solve for time using this one. So time is our unknown. In this example, we're going to actually end up canceling a whole bunch of stuff, But the easiest one for us to probably use is going to be v equals v naught plus at. We're solving for t, so we'll have vy minus v naught y over ay equals t. So I've got 12.04 negative 12.04 minus 12.04 over negative 9.8. Negative 12.04 minus 12.04 divided by negative 9.8. We get, it'll take 2.4571 seconds, or we're going to go to 3 sig figs, 2.46 seconds. So after they kick it, it's going to reach a height of 7.40 meters, and it's going to stay in the air for a total of 2.46 seconds. You could also cut this time in half, and you'll know that it will reach that 7.40 meters 1 minute and 23 seconds into its journey. And then finally, for C, we want to know at the end, how far does the ball go? How far does it travel? Well, now we have time, and we earlier up here, we resolved our vector into its components. We've got the velocity in the x direction. So now we can just do velocity equals change in distance over time. Rearrange that to get our change in distance equals velocity times change in time. Our velocity from up there in the x direction is 15.97 meters per second. Multiply that by our time, which is 2.46 seconds. Plug all that in, you will get 15.97 times 2.46. You get 39.2862, which when we round, 39.3 meters. So they'll kick the ball 39.3 meters. Now, there is a second variation of this that you can use. But let me, dang, my computer closed out. Hold on 1 second. Okay. So there is one other method or one other approach that we can actually use. Now, it only works in one specific case, and this problem is going to be the one we're going to use to demonstrate it. Scooch this back. If you start and end on same y position, you can use a special equation. And it is a very special equation. So it's so special, in fact, that I'm going to put little flashy marks around the special part. So the special equation is called the horizontal range equation. And it looks like this. Now there is a whole process that you can do that solves this and explains like where all of these numbers come from. But basically, you're going to take whatever your initial velocity is, ignoring the components, not even that part, just what the initial velocity is, multiply by sine times of the double the theta value, double the angle it's being projected at, and then divide it by the gravity of whatever it's the situation is in. So you don't actually need to have that as negative. That will actually tell you how far you will shoot something. And as a test for that, it only works if they're going to end up on the same y position. And in this case, range, this will equal the horizontal distance or the horizontal range. So going back to our football example, our V naught was 20.0. Our theta was 37. And gravity in this case is normal. It's 9.8 meters per second squared. And if we plug all of that in, our x distance is equal to 20 squared times sine 2 times 37 over gravity, or over 9.8. And if we plug that into our calculator, click on my camera, make sure you can see it. Good thing I did, because you wouldn't have been able to. We got 20 squared times sine 2 times 37 divided by 9.8. We get 39.235, or to 2 sig figs, it would be 39.2, which, going back to our other problem and looking at the answer that we got on this problem, we got that it would travel, they're both on screen, we got 39.3 compared to 39.2, which is definitely from our rounding, because we rounded a bunch of different points in there. So this equation, again, only if you start and end on the same y position can you use this equation. Now, one other unique thing that we can do is that because of the doubling portion, because of the fact that you're doubling it, that's kind of to account for the fact that there are actually two angles that will give you the same value. And what I mean by that is, let me figure out a good example of how to. Let's draw a picture to kind of show you what I mean by this. It's actually probably just easier to prove it to you with the actual equation here. So we're going to have a cannon. We've got a nice old cannon going on. And we're going to shoot our cannon in an attempt to hit a target that is 320 meters away. So our distance to our target is 320 meters away. The cannon has a speed of 60 meters a second. What angle should you aim the cannon at? So we can go ahead and plug this in. We can just rearrange. So our x is equal to v naught squared sine 2 theta over gravity. And if we rearrange all of this, we're going to get inverse sine x times g over v naught squared. And then all of that divided by 2 equals theta. Oh, sorry about that, guys. So plug that in. Inverse sine 320 times 9.8 over 60 squared, all of that over 2. So sine to the negative 1, 320 times 9.8, I'm going to put that in parentheses, divided by 60 squared, close parenthesis, I get 60.588, divide that by 2. I'm going to get 30.29, or because my values, I guess, all had 3 sig figs, we'll do 30.3 degrees. Now, interestingly, this is not the only angle that will actually work. So there's a certain point where when you fire your cannon, if I do a quick sketch of the arcs, you're going to you can angle it really, really high, and you'll get this really, really big, really tall arc. Or if you angle it really close to the ground, you could get this really low arc that also comes in. So every single way that you fire the cannon will actually have, or distance that you could shoot the cannon to, will have 2 possible values. The value that is going to give you the longest distance, though, the furthest distance, is going to be 45 degrees. At 45 degrees, at exactly half of a 90-degree angle, that is going to be the position that will give you the furthest distance. Every angle other than that, to find its corresponding angle, you just are going to go to the other side of 45. So if it's above 45, so if the first angle is greater than 45, just subtract 45. If first angle is less than 45, you just add 45 to it. So in this case, we had 30.3. Oh, sorry. No, you don't add. Sorry, that's... Hold on. Forget. That's the shortcut I tried to take last year, but that did not actually work. So ignore that. Ignore that piece right there. We are going to take 45, subtract the number, we'll get 30.3. And I will get 14.7. So since this is 14.7 degrees worth away from 45, we're going to go the other direction. 45 plus 14.7. I tried to skip too many steps in my explanation there. So if we add those two together, we'll get 59.7 degrees as our second option for it. And just to prove that that would actually end up at the same location, we can do one quick other version of the calculation there. So let's figure out the horizontal range. We're going to go at 60 meters per second, I believe is what it was, correct? Yep, 60 squared times sine 2 times 59.7 over 9.8. So you got 60 squared times sine 2 times 59.7 divided by 9.8. We get a distance of 320. A little bit over, but 320, which is the distance that it needs to travel. Now, there is a geometry explanation for this that I honestly just forgot to look up before I started recording this video. I have it written down in my explanation, my notes to give you guys in class, but I apologize. I just forgot to look it up before this because I'm a hack and a fraud. That's what I do. The main idea, though, is that you can use this equation. You can use our horizontal range equation from up here. If it's on flat level ground, if it's starting and ending at the same x position, 45 degrees is the angle you'll shoot at to get the furthest distance. And then if you move the one amount of distance up or down from 45, it will go the same distance as the opposite direction. So if you were to shoot at 46, it would go the same distance as if you shot at 44. And if you were to shoot at 50, it would go the same distance as 40. You just have to figure out the distance from 45 your angle has moved, and you can use that to find the corresponding angle that will give you the same distance. we'll work out a couple of examples of these. There's some worksheets over them. Just make sure that you are not doing this little piece that I did here. One other thing that I'll note is we mentioned this partially works because the motion is parabolic. If I go back to my football, because that was a really good example of the parabola, we made an assumption here that I just want to make sure that it is important. I actually had to add it as an extra slide last year because some people missed it. Remember, we were able to make this assumption because of the same reason we were able to make it when we threw a ball up and down. This motion is parabolic. If you know the velocity on one side of it, you know the velocity on the opposite side of it as well. So hopefully those rules make sense. If you need more explanation, just let me know. I'll be happy to kind of clear it up. This video went long and my mojo got really thrown off by that ice cream coming. In the meantime, I'm going to go eat that ice cream. Have a great rest of your day, everybody. If you have any questions, again, please send me an email. This is Mr. Diamond, signing off.